నమస్కారం విందే దాన్ని అప్పుడు আপনি থেকে মানে যে ইন্ট্রোডাকশন শুরু হবে সেটা ভিডিওটা অন করি এবারে ওই ভিডিওটা অন করে আবার হ্যাঁ শুরুটা ওই যদি সুইচ করি তাহলে অসুবিধা আপনি যেটা থেকে আসবেন সেটাই দেখাবে আমি যদি ইউটিউব দিই তাহলে আপনাকে ওই স্ক্রিনটা দেখাবে এই স্ক্রিনটা দেখাবে তাহলে দেখে দিচ্ছি আপনাকে এটাই করে হ্যাঁ তাহলে দেখে দিচ্ছি তো এইরকম ভিউটা আপনি কয়েক সেকেন্ড দাঁড়িয়ে আছে এটা থাকবে এটা এরকম থাকবে আর আমি যেটা করবো মাঝে মধ্যে যখন স্পিকার তাকে ক্লিক করবো তাতে ইউটিউব কি আমি করে দিচ্ছি একদম যে করতে পারবো আমি হয়ে যাচ্ছে দেখছি না আমি ইউটিউবের মধ্যে যে থাকবে সেই করতে হবে হ্যাঁ
Good afternoon, all of you. Good afternoon, Director Sir. So, By your kind permission, would like to start?
Yes, you can start it.
Okay, sir. Thank you, sir. Um, Respected honorable speakers for today, Professor Dr. Kamalika Sen from Calcutta University and Professor Dr. Abhijit Saha from DAE CSR, Kolkata, Honorable Director, sir, of BCRAC, Professor Dr. Piyush Pal Rai, HOD R&D, BCRAC, Professor Dr. Chandan K. Ghosh, my fellow colleagues in the organizing team, uh, and my dear participants. Welcome all of you to this national webinar on emerging applications of radiation in nanotechnology. First of all, I would like to thank the eminent speakers for today to give their kind consent to share their vast knowledge in this field of nanotechnology. After more than 20 years of basic nanoscience research and more than 15 years of focused R&D, applications of nanotechnology are delivering in both expected and unexpected ways on nanotechnology's promise to benefit society. Nanotechnology is helping to considerably improve, even revolutionize many technology and industry sectors, information technology, security, medicine, transportation, energy, food safety, and environmental science, among many others. Several methods have been developed to produce metal nanoparticles. Two synthesis approaches have been identified, that is top-down and bottom-up approach. Top-down methods comprise of milling lithography and repeated quenching. This approach does not have good control of the particle size and structure. Bottom-up method is the approach that is mostly used by scientists in the synthesis of nanoparticles, as it involves building up a material from bottom, atom by atom, molecule by molecule, and cluster by cluster. Several chemical routes have been identified to synthesize the colloidal metal nanoparticles. The chemical routes that have been studied for various applications include electrochemical method, sonochemical method, radiolytic, and photochemical method. Gamma radiation is the preferred method for metallic nanoparticles synthesis because it is reproducible, it is easy, it is cheap, and use less toxic precursors in water or solvents such as ethanol. It uses the least number of reagents. It uses a reaction temperature close to room temperature with as few synthetic steps as possible and minimizing the quantities of generated byproducts and waste. With these few words, I would like to invite Professor Dr. Piyush Pal Rai, Director BCRAC, to formally welcome the eminent speakers for today, Professor Dr. Kamalika Sen from Calcutta University, and Professor Dr. Abhijit Saha, Director DAE CSR, Salt Lake, Kolkata. He will join at 3 p.m. of course. Now, it's over to you, sir, to welcome the speakers. Thank you.
Thank you, Professor Ghosh. I heartily welcome all the participants in this one-day national webinar on emerging applications of radiation in nanotechnology. I'm very happy to see taking place in a very emerging field, that is the nanotechnology, as Professor Ghosh has already told, that it has immense applications in IT sector, security sector, energy sector, environmental science, food sector. I am thankful to both the very eminent speakers, those who are very much expert in this particular area and have been doing their research for the last 2 decades, more than 2 decades, of course, for giving their very important time to us to listen to them. Professor Dr. Kamalika Sen, she is an assistant professor in the University of Calcutta, assistant professor of chemistry department, and Dr. Abhijit Saha will be joining soon, that Dr. Ghosh has already told, that is the Center Director, UGC, DAE, CSI. Now, why this nanotechnology is required actually? Because you see that if you like to do some very specific research and research to the lowest scale, because you see that nowadays the medicines, if you see the medicines also, this nanotechnology has got immense applications in these medicines. And that's why you will find that nowadays many of the antibiotics are coming, which are actually the people are using it at a lesser number, but the actions is much more because the technology is simply nanotechnology. So, but we were not aware actually what is the applications of the radiation in this nanotechnology. So the subject is of course a new subject for us. Listen to the learned speaker. I thank the Basic Science and Humanities Department for conducting this very important webinar, as well as our R&D sector headed by Professor Chandan Kumar Ghosh, who is heading this R&D section. And actually, the main intention, I am just requesting Dr. Kamalika Sen and Dr. Saha both, because you see that this particular college has got a very good, actually, footprint in this state of West Bengal. There are many reasons for that one. Our academics is very good. Our infrastructure is very good. Our quality faculties are also very good. So we like to do some collaborative research as well, because we have also very learned faculty, those who are actively engaged in research in different organizations. But I want to, I want some collaboration so that this college particularly can take part in this kind of research. And that is only possible with the collaborations of universities like IISER, then Calcutta University, Jadavpur University, University. With that expectation, I hope that Dr. Sen will get, whenever this pandemic will be over, you will make a personal visit in this campus and have interactions with our colleagues, and so that we can find out some common path where we will conduct some research and both the organizations will be benefited out of that. With these few words, I welcome you once again, and over to Dr. Ghosh.
Thank you, Dr. Pijus Palrai, sir, Director, sir.
I want to thank your other colleagues. I
Yeah.
also thank your other colleagues, those who are here actually. I am not specifically mentioning their name, but the Saurav Janman Das is there. Then we have then another
Super.
here. So I thank all of them, not only you, but all of them of the Basic Science
Thank you,
Department.
sir. Thank you,
What
sir. Yeah. So now I would kindly ask Professor Dr. Shukalpa Dev, who is an assistant professor in our department, chemistry department, to take over and introduce our esteemed speaker, Kamalika Sen, Dr. Kamalika Sen, to all the participants. Over to Shukalpa Dev, Dr. Shukalpa Dev.
Thank you, Abhijit. And first of all, I welcome Dr. Kamalika Sen to give the permission for her speech. And before that, I just give some brief CV about this about ma'am. And just I want to say, Dr. Kamalika Sen is working as an assistant professor in the Department of Chemistry, University of Calcutta since 2010, that means 2010. Her main research interest is in the field of analytical chemistry. Her research topics entitle different aspects of the subject like development of green methodology for speciation of elements in the ultra trace scale, exploring different aqueous two-phase extraction systems, separation of protein fractions from peanut and their interactions with metal ions, developing green methodology for synthesis of nanoparticles and effect gamma radiation. Currently, her interest is focused on development of different porous materials. She has received various grants from UGC, DST and UGC DAE for her research. Till now, 8 students have obtained their PhDs under her supervision. She is currently supervising 4 PhD students and 2 postdoctoral fellows. She has publication around 106 articles in international journals. So, welcome, ma'am, and over to you, ma'am, for your deliberation. Thank you, everybody.
Very good afternoon. This is a great pleasure to join this webinar. First of all, I would like to thank Director Sir, Professor Piyush Pal, and very thanks to my friend Dr. Abhijit Ghosh. And I would also like to thank Shukalpadi. Shukalpadi is my senior from Hugli Mohsin College. I hope she remembers me. Shukalpadi, do you?
Yes, I remember
Okay.
you.
So it's a matter of great pleasure that I can see you after such a long span of time in such a webinar, but it would have really been nice if I could have been there at your institution for this conference, but yeah, the situation is not right. And Abhijit, I have also not met you for a long time. Would have also been nice to meet you there, but still it is better that I can see you together in one platform, and it would also be nice to have good collaborations as director sir has requested. And in today's presentation I would like to share some of my experiences that I have been going through since last almost 20 years. But in the beginning it was just a little bit baby steps like that, because nanotechnology before 20 years was not flourishing that much, and it was just a little bit nonsense type of research. But I would start from there so that you can have a flavor that how it gained importance slowly. So without wasting much time, I would directly switch to my presentation. Can you see my screen?
Yeah, yeah, we can see, we can see.
Okay.
Yeah.
Gamma irradiation mediated sustainable synthesis of metal nanoparticles is my topic today. Uh, Gamma radiations do accompany several nuclear decay processes that occur spontaneously in the nature. So one can easily consider these energetic radiations as a natural phenomenon which is available in abundance in the nature. But one has to avail it in a very secure way. Having enjoyed a long time working in a radiochemistry laboratory, rather different radiochemistry laboratories, I have felt that gamma rays are underutilized even today. I feel it is a self-sufficient and self-propagating continuous source of energy that can have far-reaching vital applications. It's us who need to dive into the intricacies of the methodologies to find out its astounding capacities. So I think I should start with the initial days of my research where gamma radiation was found applicable. Let me start with a story when in a radiochemistry laboratory of Saha Institute of Nuclear Physics, when we were trying to extract some radioactive isotopes of gold using aqueous biphasic systems. I was shaking and I was trying to make some solvent extractions using 198 gold isotope. Normally we used to do the experiments, and after finishing the experiments in the evening, we had to clean all our apparatus by dumping and just accumulating our radioactive wastes in a separate container that was to be treated in a separate way. and clean all our apparatus in a pre-trained manner and then go home. But that evening, I was in a hurry and it was about 8 or 9 in the evening, and I forgot to clean my apparatus which contained the gold 198 isotope. I thought, okay, the next morning I would go very early in the morning and clean before other lab mates and my guide appears, and I would clean and nobody would know. So the next morning I came in the lab and found that my gold solutions, which were supposed to be golden yellow in color, turned pink um, all over. So I thought, who came in between and added something to my solutions? How it happened? I was just stunned. So at that time, it was about 2005 or so. All of us did not have mobile phones, and I had to wait until my lab mates came, and individually I asked everyone who had made my solutions pink and who had added something to my solutions. I don't know. But no one said, no, you yesterday you left the latest and today you arrived the earliest. So you must have done something. So that day I did not make any other fuss, but I cleaned my apparatus and did my next experiments. And but something struck in my mind. So that day I deliberately prepared a gold solution in a similar way and put it at the back side of a cupboard so that no one could see, and left it again for the next day. That same day also it appeared pink. So that now remains questionable. What happens to the gold solution that golden yellow color turns to pink? So nano never came to mind in 2005. So then slowly one or two lab mates of me were started laughing. Your solutions are playing tricks. And then after 2 to 3 days, we together, I was not courageous enough to report this thing to my guide alone. 2 or 3 of us went together and told my guide that this is happening for last 2 to 3 days. So he took a pause for a moment and said, have you heard about gold nanoparticles? They appear pink in color. Then we said, yes, we have heard, but I haven't used any reducing agent, and it is only auric chloride. How can it get converted without any reducing agent to gold zero? Then he said, you must be doing something new. You must check it out. So then we started doing experiments and we studied a lot of papers on the gold nanoparticles. And because our gold isotope 198 gold was having a half-life of 2.6 days, and we could easily allow it to decay for 10 half-life, that is more than 20 days, 20-25 days. And then we can go on for analyzing it for different TEM, UV, etc., because we will be taking it to the apparatus which will be used by others. They may have objections in introducing radioactive samples in it. So we had to wait for 25 days to decay out all of the radioactivity. So this was the radioactive gold nanoparticles, and we had checked from the literature that gold nanoparticles do appear pink when it is very small in size, and the color varies, color intensity and color, the tint of color changes from pink to bluish with the increasing size of gold, and the nanoparticles of gold can act as tiny, precise and powerful heaters, which potentially could be used in biomedical applications by using biolinkers. The nanoparticles can be designed to affect specific targets such as tumor cells. These all came from the literature later on, but at that moment we didn't know all about these things. Even earlier men, we have studied from literature that earlier men, something around 200 or 100 BC, people used to decorate the window panes of churches in the European countries using gold nanoparticles, because color was content at that time, and people did not know that they were using gold nanoparticles. Later on, it was established that those colorful designs in the window panes of churches were made of gold nanoparticles. simple setup of gold nanoparticle extraction was 50% polyethylene glycol water solution, then mixed with sodium sulfate solution, and that was shaken with gold 198 aurichloride salt solution. Then shaken, I was trying to separate the salt rich and polymer rich phase and trying to do the gamma spectrometric analysis, but the current, it made nanoparticles, and we had to settle it 5 days so that it it decays out of the radioactivity, and then we put it into the UV visible spectrophotometer that shows a characteristic surface plasmon resonance peak, and the 10 images showed 20 to 30 nanometer sized particles. A similar solution prepared with stable gold solution gave very large particles. You can see the scale, and this is not a particle actually. This is a patch, and this does not form any kind of nanoparticle. Here, I would like to mention that after this pink color incident, our radioactive gold, which was brought from BARC, also the whole thing was decayed after some 1 month or so. So my experiment was over. I could not do any further experiment. So I thought, okay, if gamma is the responsible thing, we have a gamma chamber in our institute. Saha Institute itself had a gamma chamber at that time. So I prepared my sample solution and put it inside the gamma chamber so that gamma radiations will make my nanoparticles. But that was a failure. That did not prepare the nanoparticles. Later on, I will come to it. So we thought that the reactions taking place in the solution were the reduces of water that led to the production of hydrogen and hydroxyl free radicals that eventually reduced the cation. After the gamma chamber experiment, we deduced from it that gold 198 is short-lived, has half-life of 2.69 days, and has high intensity gamma energy at 411 keV, much less gamma energy, which is different from the cobalt 60 isotope that was in the gamma chamber. And in addition, it also provides beta decay energy from 1.3 MeV. Beta decay means that provides a lot of electron density inside the solution, which is responsible for the reduction of gold. Thus, radioactive gold nanoparticles may be useful for in vivo and in vitro applications where both the properties of nanoparticles as well as high energy gamma ray and beta emissions will be useful. So, because it was very early and at that time only preparation and characterization of nanoparticles was enough to have a good publication, and we did not have any difficulty to publish this thing. Much of the observation could be easily published, and then we tried with the generation of a gold palladium bimetallic nanoparticle, where instead of the gold solution alone, we just added palladium together with gold and tried to have some kind of application. Similarly, just like the previous set, we added palladium chloride solution to it and did the similar experiment. And after decaying for 25 days, we found that the absorption spectrum shows no peak in the visible region. And this is actually the characteristic property of a palladium containing solution, which does not show any peak, any surface plasmon resonance in the visible range of the UV spectrum. This agrees with several palladium nanoparticle previous reports, and this is actually the property of palladium nanoparticles which matched with our observation. This was the 10 image which showed very small particles. See, you can see 2 to 3 nanometer size gold palladium bimetallic nanoparticles. If I zoom in, you can see a darker shade, which is possibly because of the gold, and the light shade, which is because of the palladium, and even mixed type of shades, which shows there are also presence of alloy type nanoparticles. This is the closer view, and the energy dispersive X-ray analysis says that there is a higher percentage of in the mixture than gold. And the overview is that without the presence of any kind of hazardous chemicals, we all know, only with the radiation in the solvent, it can generate the nanoparticle. This thing also is not possible with external gamma radiation. Only in situ gamma dose is responsible for the bimetallic. So next we try to see if bioreagents were also capable of generating the nanoparticles. We selected the yeast cell. The biologists call Saccharomyces, and we just put the yeast cells in a gold aurichloride solution. Our same solution of aurichloride containing 198 gold, and after, so you can see that gold starts entering into the cell, and as soon as it starts entering into the cell, small bits of gold nano formation have started. With time, say after 1 hour, small particles have entered the whole of the cell. You can see very small particles throughout. It has just clouded the surface of the cell. This is a thin section of the cell. After 24 hours, the particles have grown in size. These are larger. There are also smaller particles, but some particles have started growing in size. After 48 hours, more of the particles have started growing in size. Then after 72 hours, see, there are more larger particles, and the particles have entered into the nucleus of the cell, and precise inside the nucleolus part of the cell. This is the nucleolus, which is the main, which is the main part of the nucleus. A similar thing.
I just want to submit one humble submission that there are many actually participants, those who does not know actually what is nanotechnology. If you can throw some light on nanotechnology, because you know that people say that the hair, our hair actually, it has the dimension of 80,000 actually nanometer. So we would like to know that what is nanotechnology and why it is required and why it is refined technology. If you can throw some light, that would be better for the participants. Before you do high-end research. Okay.
Okay. So this thing actually, I was trying to describe my previous experiments and how it slowly got shape into the modern days nanotechnology, how it took the shape. That much I was trying to explain. For that reason, I started so early. So I think for that, they have to wait until the end of my presentation. Is that okay, sir?
Yes. Yes, it's okay.
So this is the macros for the stable gold solution. We can see there are no nanoparticles and nano particles of gold. They are not transmitted to the future generation yeast cells, the thin section of the budding yeast cells, and we can see that if this cell was initially accumulating the gold and converting it to the nanoparticles, it is not transmitting it to the next generation yeast cells. So what can we expect from this type of observation? The overview says that radiation can also generate gold nanoparticles within the cell, NPs within the cell, nanoparticles within the cell. They are genetically not transmitted, and the technology is the radioactive gold nanoparticle may lead to future scope in yeast-inspired drug delivery, where biotechnology meets bioengineering and synthetic biology. I hope your students have heard about drug delivery by some bioreagents where yeast is also used as a drug delivery reagent. Have you, my dear students? There are many alternative drug delivery reagents which are used to treat patients, and gold 198 is one such drug. and that is used for the treatment of rheumatoid arthritis. And if it is in the nano state, then it has some other added advantages that you may be knowing in your engineering classes or maybe from the literature. And if it is incorporated in a kind of edible cells, yeast is edible, as you may know, it is present in our bread. And if it is given in that kind of cell, then that is also possible to have drug delivery application. And this kind of things are the new generation drug delivery system. So that is the very upcoming part of research. So up to this point, you may have noticed that I had made my slides in black and white, and this was the flashback era. Now I am coming to the present situation, where how I have used the external gamma radiation to modify the prepared nanoparticles, and how they are used for the advancement of so-called technology. In my case, I have used in developing some analytical aspects of chemistry in terms of chemistry lookup. So the first part of this kind of work is the peanut skin polyphenol mediated synthesis of iron oxide nanoparticles for anion sensing of perchlorate ion. Okay, so for this, first we synthesized the amorphous iron oxide nanoparticles, then characterized, studied the physicochemical modification upon low dose gamma irradiation, and then spectral sensing. Now, the flashback era, what was discussed earlier, was fortunately that work was done with my own hands, but from this part onwards, this part is done by my students. So I have to listen to them, and I have to give priority to their thinking, because they are doing their PhDs, and I have to support their thinking also. So students say that we would like to use polyphenols, as in my laboratory it is not possible to use radioactive isotopes. It is not a DAE permitted radioactive supported laboratory, just a chemistry laboratory. So I can use radiation in a radiation chamber, take it out and use for chemical purposes, but not the use of radioactive isotopes directly is allowed in my laboratory. So the reducing agents used for generating nanoparticles are polyphenols, which are abundantly available in different natural substances. Polyphenols, they are actually reported to generate different metal nanoparticles like silver, palladium oxide, nickel, zinc, gold, iron, and so many other things. And they have, polyphenols have other applications like antioxidant, UV protection, anti-cancer, and so many things. And what thing we have chosen is a peanut skin, because we have had our work with peanuts, peanut proteins, throwing out the peanut skin, which releases an excellent red color when soaked in water, and that red colored solution contains a lot of polyphenols. So if that polyphenol is utilized towards generating nanoparticles, would really be very helpful, because for that we are not purchasing any kind of chemical. It is cost effective, it is not hazardous, and many other things, and it is also aqueous. So it is also a good reducing and stabilizing agent towards nanobiosynthesis. And somebody in the previously reported literature have reported the presence of so many polyphenols in this peanut skin extract, and this has been listed here. You can see the structures of these kind of polyphenols. We have chosen the generation of iron oxide nanoparticles because they also have reported to have different applications, mainly in the biomedical industry, like Fe3O4 together with manganese dioxide is seen to have MRI contrast property. They also have semiconductor property, magnetic data storage, catalysis, pigment, gas sensing, coating, lubrication, solvent. Only iron oxide has so many applications. So once we can generate, if we can generate these kind of nanoparticles using this cost-effective reagent, then we can have some kind of application which will be very useful. So for that, we have taken 2 gram of peanut skin, taken in 100 ml distilled water, soaked overnight, and the red colored solution was filtered, and the filtrate was adjusted to pH 3, and to that we have added 5 millimolar of ferric nitrate. The yellow color of the ferric nitrate then and then changes to brown, and then to green, and then to black, indicating the formation of iron oxide nanoparticles, which we call set A, which is prepared without the application of gamma irradiation. Similarly, if the set A is put inside this gamma chamber for 15 minutes, we call it set B. And if we keep it inside the gamma chamber for set C for 24 hours, that is called set C. At that time of irradiation, the dose rate inside the chamber at UGCDA ECSR Chingrigata was 2.989 kg per hour. So the UV spectrum of the solution that we have used after adding iron shows the characteristic surface plasmon resonance at about 430 nanometer, which is its characteristic peak. Increases with increasing concentration of iron. The XRD pattern, this is the powder XRD pattern, we can see, students, you can see that there are no sharp peaks. What does it mean? If there are no sharp peaks in the XRD pattern, I hope you believe that the powder XRD, if it shows sharp peaks, then it designates some kind of crystallinity in it. So if there are no sharp peaks, then we can call it amorphous, isn't it? So amorphous is the kind of nanoparticles that we have generated. And if you go very nicely through the literature, you will find that there are many articles that report on the production of crystalline iron oxide nanoparticles, but report on amorphous iron oxide nanoparticles are less. However, the application of amorphous kind of nanoparticles is high, which is because it has very high surface area, and the higher surface area makes it very much suitable for higher surface activity, higher absorption, higher application as catalysis as the surface becomes available for reactions. This is the Raman spectrum, and the Raman spectrum after irradiation, we can see here a new peak, which is because of the presence of carbonyl group. A lot of carbonyl group was present inside the polyphenol, and which gets bonded with the iron, and this is after the irradiation, because the irradiation causes radiolysis of the polyphenol and breakage of some carbonyl groups, which is now getting bonded with the iron, and metal carbonyl bond is formed after irradiation. And we can see the TEM images. We can see before irradiation and after irradiation, the particle size has reduced. After irradiation, the particle size actually reduces because in presence of the energetic beams, the particles do not get the preference to agglomerate very easily. That is why the particle size is generally less if it is prepared in presence of irradiation. This is the FTIR spectral data. This is the PNS, peanut skin extract. You can see a lot of carbonyl group stretching vibration in presence of only in PNS. However, in set A, which is prepared in absence of gamma irradiation, the carbonyl group is less. That means with the solid, the involvement of carbonyl group is less. However, with irradiation, because of radiolysis and the breakage of the bonds, carbonyl moiety is more available to the metal, and more of the carbonyl is attached to the metal. And FeO stretching frequency is also available here, somewhere in 670 or 537 centimeter inverse. Now what we used is since my interest is with analytical chemistry, so I have used this substance for anion sensing, and for we have seen preference for the perchlorate ion. Perchlorate reduces thyroid hormone. The most astounding feature with the perchlorate ion is that it has a high similarity with the iodide ions. Iodide is very similar in structure, in size, in property with perchlorate. So it replaces the thyroid hormone site where iodide gets attached and disrupts the thyroid function. And some studies suggest that perchlorate has pulmonary toxic effects. These are the actual results where 2.2 milligram ions, ions means iron oxide nanoparticles, and 2 ml salt solution, 1 millimolar was mixed and soaked with the supernatant. We have treated with different anions. Can you excuse me for 1 second? So with fluoride, bromide, iodide, sulfate, nitrate, and sulfide, the absorbance was not very high. However, with perchlorate, the absorbance at some 290 or 300 nanometer, the absorbance increases sharply, which means that in presence of some other anions, perchlorate can selectively be sensed. Here 300, near 300 nanometer, selectively for perchlorate, there is a high absorbance peak, which is different from the other anions. And for the non-irradiated nanoparticle, the blue one, the absorbance value increases at higher concentrations of the perchlorate, 100 millimolar, 1000 millimolar. For 15 minute irradiated nanoparticle, it increases at a little bit lower concentration, but with 24-hour irradiated nanoparticle, it starts with the very low concentration of perchlorate, and the sensing ability starts with a very low detection limit, and the linearity is also good for the set C, as we can see here. The SEM analysis shows that the surface of the non-irradiated sample, that is set A, is flat. However, the set B, we can see very small sized particles. It is 50 minutes irradiation, lesser size in 24 hours irradiation. With the perchlorate treated set C, there is no change in the morphology. That means perchlorate quietly sits without changing the morphology, and we can see the effect of irradiation very nicely, that the particle size has grown very small. And we can also see the perchlorate treated iron oxide nanoparticles. We can see the peaks for perchlorate, and the iron nanoparticle treated perchlorate, it actually enters, it has high oxidation power. It actually breaks the iron oxygen bond and forms perchlorate. That is why we see the change. So these are the findings. The amorphous products found in each case were found to be efficient for selective sensing of perchlorate ions amongst a set of 7 ions. The sensitivity for perchlorate increases as the time of irradiation increases, which is an outcome of increased surface activity upon exposure to irradiation. The method highlights an economically viable method for nanoparticle synthesis and opens an avenue for novel analytical applications. The second part is the use of a block copolymer. This time we have not used, students chose to use a biocompatible block copolymer for synthesis of palladium quantum dots, and that they have used for the reduction of chromium 6 to chromium 3. They have synthesized, then characterized and calculated them to observe the mechanism of nanoparticle formation, and check the environmental feasibility for a reduction of toxic chromium 6 to safer chromium 3. and that also in presence of gamma irradiation. So there are many Nobel group quantum dots reports available in the literature. These are platinum, palladium, rhodium, ruthenium, iridium, osmium, but our selection was palladium because palladium has high surface reactivity, good melting point is high, high purity, shape is almost uniform, and crystalline, they have good crystallinity and they have good electronic properties. Also, these quantum dots have catalytic properties, they have electronics. They are also reported to have been used in electronics as biosensors in medicines, light emitting diodes as semiconductors, and so on. And people have used different conditions in generating palladium quantum dots. You can see heating at 100 degrees Celsius for 5 hours, stirring, refluxing, then pressurized system, use of pressurized system, then 2 hours time which is required at room temperature, 180 degree, so many conditions. But in this particular system, we need only 5 minutes at room temperature in presence of the block copolymer to produce the quantum dots. Actually, block copolymer generates micelles with only 0.6% weight by volume concentration, and the CMC can be measured by the conductance measurement. And if we take 1 ml, only 1 ml of 1 millimolar palladium 2 plus solution and add 1% block copolymer solution, keep it just for 3 to 5 minutes at room temperature, the color transforms from yellow to brown, and this is the visual change, and we can also see it using absorption spectra. Absorption spectra of palladium 2 plus solution. This shows a peak at 420 nanometer absorption spectra, and after palladium quantum dot formation, we can see that there is no particular surface plasmon resonance in the visible region. This observation was also observed in our flashback era. So we can see that the palladium quantum dots has been formed with 2 to 3 nanometer size particles. These are the crystallinity showing SAED pattern, showing crystallinity, showing fine annular rings, and this is the dynamic light scattering and zeta potential results. DLS results shows a higher size than the actual TEM dots. This is because of the hydrodynamic radius. This is the compatibility of the instrument. Actually, I tell to the students who are getting introduced to the nanotechnology that if you can place a grid on which you have put your nanoparticle solution and allow the electron beam to fall on it, the shadows of the nanoparticle fall on your experimental plate. But if you take the nanoparticle containing solution in the DLS setup, which is just like a UV visible setup, then you will measure the hydrodynamic radius. That means the nanoparticles surrounded by the hydrated environment. So the overall size seen by the instrument is higher. So you can see that there are particles with more than 200 nanometer size. That does not mean that your particles are of 200 nanometer size. They are surrounded by the hydration actually. And the zeta potential measurement, the electrical double layer measures the potential around the nanoparticles, which increases upon palladium quantum dot formation, which indicates the formation of nanoparticles. And if the zeta potential value increases either in the negative or in the positive direction, that means that the electrical double layer has formed, and that means your nanoparticle has formed in the solution, and that particle accumulates the electrical double layer on its boundary. The conductivity also increases as a result. Now this is the way how the kinetic measurement is done. This is the Finke-Wadsky model. Here we can see our method. First, it's a very fast process. We have seen that only 3 to 4 minutes is sufficient. So if we see a time scan for about only 100 seconds, we can see only after 10 seconds the nucleation process has stopped. That means the stable region is finished after 10 seconds. Then there is a slow and steady growth, which is the autocatalytic growth, and it attains a steady state after 100 seconds. This is the autocatalytic growth. So first there is nucleation all over. Nucleation means small particles, they are generated all over in the solution, and each particle that has generated, see here, palladium 2 plus block copolymer that has reduced block copolymer has reduced palladium 2 plus to palladium 0, and there is the presence of palladium 0, which autocatalyzes itself to again more particles, and that results in the growth of the particle. So this is the autocatalytic growth phase, and if I call this rate as K1 and this rate as K2, and then I express these two in the equation, the two equations can be combined as in equation 3, and we can express in the form of a linear equation like this. And if we can plot a graph, we can see that for our case, K1, that is nucleation part, is almost constant. The values are not changing much, but the K2 value that is dependent on the concentration of palladium, which is varying using this equation. The FTIR spectra of the block copolymer, when compared with that of the palladium quantum dots, we can see that they vary only little. There are no new kind of peaks appearing. This means that palladium quantum dots, palladium does not form any kind of bond with the block copolymer functional groups or moieties. This is only being stabilized or encapsulated in the micellar system of the block copolymer. Now we have chosen chromium 6. I will not discuss here much because we all know chromium 6 is toxic, chromium 3 is essential. We would like to reduce chromium 6 to chromium 3, and that too is done in presence of some kind of concentration of acetic acid is used, and here we have seen that with increasing concentration of acetic acid, absorbance decreases, and with time also absorbance decreases. That is, high acetic acid concentration increases the efficiency of chromium 6 to chromium 3 reduction, and same as with time. And this is the reduction of chromium 6 to chromium 3. This is the reduction. With increasing of palladium quantum dot, there is not much decrease in chromium 6 to chromium 3. Here we have tried to find out a rate equation where with increasing concentration of chromium 6, we have plotted different time scans. So this is, if this is with 1 millimolar chromium 6, this is with 0.5 millimolar, this is with 0.3 millimolar, and so on. So we can see that the rate is decreasing with decreasing concentration of chromium, and if we plot the log of the rate with log of the concentration of chromium, we get a plot like this. And if we have an equation like this, from the intercept and slope, we can get the order of the reaction. This is the order of the reaction, which is almost 2, and the rate equation shows that the reaction is dependent on the chromium 6 concentration and on the acetic acid concentration. That means palladium is acting as the catalyst only. Now, what is the role of gamma irradiation? Now, remember, we are using a costly metal palladium to reduce chromium 6 to chromium 3. So, we would like to regenerate the palladium catalyst after every use to the fullest. So, if we just use the catalyst without the use of irradiation, we will see that our reaction does not go to completion. That means chromium 6 is reduced, but it is not reduced to 0. After first cycle, after second cycle, after third cycle, its efficiency decreases. But if we compare it with the irradiated sample, if we take the chromium-6 solution, add the palladium quantum dot and put it in the gamma chamber, take it after some time, we will see that the reaction has gone to completion. The whole of chromium-6 has been reduced, as well as the palladium quantum dot has settled down to the bottom. So we can regenerate our costly palladium nanoparticle after the use. So it is yet another application of gamma irradiation where we can have some other feature. So this is the conclusion that 2 to 3 nanometer particles have been attained, which can reduce chromium-6 to chromium-3, and these are more effective when done in presence of gamma irradiation. But how much time do I have? Okay, so I have more minutes. Yeah. If I have 10 more minutes, then I would like to discuss the last part of this work.
No problem at all, ma'am. You continue.
Okay, thank you. So this is the last part. This is the designing of porous ruthenium Morin nanocomposite and the role of irradiation on it. During our experiments in the laboratories, we have seen a very difficult task that the lanthanoids have very similar ionic radii, and because of their similar ionic radii, they have very similar chemical properties, and because of this very similar chemical properties, they are very difficult to separate, isolate, and it is very difficult to identify each of them if they are found in combination with one another. So it is a very challenging task to identify a particular lanthanide in presence of the other. And also lanthanides are finding applications in many kinds of technology nowadays, and they need to get recovered, they need to get detected, they need to get reused, and so on. And the methodology for their detection is very difficult because of this lanthanide contraction problem. So we tried to see if our nanoparticle systems or irradiated nanoparticle systems can be of any help in solving this kind of problem. So we synthesized a new nanoparticle, ruthenium Morin nanocomposite, via a green process. We have characterized an application, found application towards sensing of some lanthanides. The method was also like the previous ones. It was a green methodology to synthesize the nanoparticles, and we have used Morin as a capping agent. What is Morin? Morin is also a polyphenol. It is naturally occurring polyphenol, and it occurs in the leaves of the common guava, but we have not extracted it from the leaves. We have bought it pure from Sigma, and we have prepared the nanocomposite in absence and in presence of gamma irradiation. We have taken 5 ml of 10 millimolar ruthenium chloride solution and mixed it with 5 ml 10 millimolar Morin solution, adjusted the pH to 12 and settled it for 12 hours. This is our set A, which we call non-irradiated sample. Similarly, we have taken the solutions just like the previous ones and irradiated it for 24 hours in the gamma chamber. Now the dose rate in the gamma chamber was only 1.59 kilogray per hour, and all the nanocomposites were collected after several washing with water alcohol mixture and dried under an IR lamp. Then we characterized it, and yeah, this is the characterization. This is the absorption and emission spectroscopy. We can see it is a little clumsy. This is the absorption spectrum. We can see at 330 nanometer, ruthenium shows increase in absorption peak with addition of, Morin shows a 330 nanometer absorption peak, which increases with addition of ruthenium-3. And if we try to plot the Benesi-Hildebrand plot, we can find the association constant between Morin and ruthenium. That means there is a sort of complexation occurring between ruthenium and Morin. Since Morin has fluorescence, we can also see the fluorescence quenching of Morin in presence of ruthenium, and we can also see the Stern-Volmer quenching constant here. This is the quenching plot. Here here the mechanism of nano formation is slightly different than that of the palladium quantum dot formation. Remember, this is not the quantum dot, this is nanoparticle. Now I would like to tell the students what is the difference between a quantum dot and a nanoparticle. Nanoparticle is something which has one of the dimensions in the 100 nanometer size, and quantum within 100 nanometer size, that can be anything between 1 and 100, but quantum dots also fall under the category of nanoparticles, but they should be one of the both the dot, you know, it is dot, so it should be three-dimensional, and all the dimensions, it should be within 10 nanometers. So we have our particles of 3 to 5 nanometers, so they are definitely quantum dots. They are very small, so normally they do not aggregate, they do not form precipitate, they do not isolate out from the solution. So once they are formed, it is very difficult to take them out from the solution. So once you have applied them for your practical application, you cannot regenerate them until you do something great like gamma irradiation or so. So these are ruthenium morine nanoparticles. These are not quantum dots, but they are nanoparticles. These are formed using a two-step mechanism. First part is the Lamar mechanism, and the second part is the Finke-Weizke mechanism. How is the Lamar mechanism doing? This is characterized by the formation of nanoparticles by nucleation. First is the nucleation. This is the small particles in the solution. It is developing due to reduction of the metal, formation of nanoparticles, and that kind of nanoparticles are slowly being generated inside the solution, and then this falls, the peak falls. This is called the burst nucleation part, where this means that the formed nanoparticles, they aggregate. The previous one for the palladium quantum dots, it was autocatalytic growth. One nanoparticle catalyzed the formation of other nanoparticle on its surface, but here the formed nanoparticles, they individually come closer together and aggregate. So this kind of peak falls sharply. Once it starts falling, after some time, then starts the autocatalytic growth. This means here this part starts the Finke-Weizke mechanism. So on seeing the absorbance versus time plot, you can simply deduce what kind of mechanism is going on inside your solution. Now with the particles, we have tried to see what is the pore diameter. We can see with set A, that is with non-irradiated sample, the pore diameter is higher. With set B, that is with the irradiated solution, pore diameter is less. But the bed surface area, the total surface area is however a little less for set A and little more for set B. This is because of the lesser particle size of the irradiated nanoparticles. See from the TEM image, lesser particle for set B is visible here. The set B, the annular rings, the microcrystallinity is visible from here. And this is the histogram. You can see particle distribution. The non-irradiated sample is little larger. The irradiated one is little smaller. And from the FTIR spectrum, here it is complex formation, unlike the palladium quantum dot one, and we can see that there is metal carbonyl bond formation. See here in this pure morine, 2060 to 1805 centimeter inverse. There it is. Here there is generation of new peaks. That means there is metal carbonyl bond formation in both set A and set B, and in set B there is more, the peak intensities are higher than in the case of set A. That means more of carbonyl group is involved in the bond formation with the metal. Powder exciting, we can see here this is also amorphous, as there are no peaks in the powder exciting pattern. And dynamic light scattering experiment shows higher diameter although the trend is same. That means the irradiated particle is lower in dimension than the non-irradiated one. And for the sensing case, we have chosen 6 lanthanoids: lanthanum 3, cerium 3, cerium 4, cerium 3, samarium 3, gadolinium 3, and dysprosium 3. You know how difficult it is to collect different lanthanum salts. Either they are too costly or they are not available in the market. They are very difficult to isolate also. So we could gather only some of these salts, and we have used different pH solutions. We have used the set A, our set A and set B, and we have used only UV and fluorescence spectroscopy, and the lanthanoids for pH dependent sensing. See, cerium 4, for cerium 4 spectral sensing, we have seen 4 conditions. For absorption spectra, pH 2, pH 7, and pH 12, we can see different peaks which increase with increasing concentration of cerium. That means with increasing concentration of cerium, the absorption spectra show increasing peaks at 253 and 293 nanometer at pH 2, at pH 7 at 293 nanometer, and at pH 12 at 320 nanometer. If we see the fluorescence spectrum and excite it at 290 nanometer, we can see an emission at 391 nanometer at pH 7. It also shows a turn on fluorescence in presence of cerium 4. For dysprosium 3, we can see only absorption spectral sensing with a peak at 293 nanometer. For cerium 3, we can see absorption spectral sensing at absorption peak 320 nanometer, and using all these three, we can actually sense, quantify, and individually separately sense these 3 metal ions. For overall sensing, we can see the limit of detection at 0.09 micromolar, which is almost 90 nanomolar. That means the lowest limit of detection is at pH 2 using absorption spectrometry, which is only 90 nanometer. And using other pHs, you can also do it, but the limit of detection is little poor. So we also have a good linear range for all the systems. For dysprosium 3 and cerium 3, it is 5.37 and 0.08 micromolar. And now we try to sort out a plausible mechanism, because every observation needs to have a good explanation for its mechanism. Otherwise, it is very difficult to publish nowadays. Earlier, it was only sufficient to just generate nanoparticles and characterize them. Now you have to do application and see the result, and then find out the mechanism, and then prove and establish, and then everything has become a little difficult. So due to very high reduction potential, 1.72 volt of cerium, it can easily oxidize ruthenium morine at all the pH. Gamma irradiation cause cleavage of the MO bond and generation of free radicals and active species. Cerium 3 remains as the hydroxylated cerium species, pH 12, due to high basicity of the species. It can donate its electron density to the ruthenium morine species, and as a result, the absorbance intensity increases. For dysprosium at pH 2, it carries a very high effective nuclear charge of 8.85, which is higher than the other ions. And at pH 2, the OH moiety of morine gets protonated and remains surrounded by the active free electrons. The sterically crowded ruthenium morine environment now can be invaded only by the small, highly charged dysprosium 3 species, and hence can be sensed. So neither gamma irradiated morine only, which is the mother solution, or ruthenium chloride solution alone is capable of the sensing of the lanthanides. Now we have studied the interference from other ions like iron, cobalt, nickel, copper, zinc, lanthanum, samarium. Absorbance shows no kind of interference. Same results remain almost the same in presence of the interference. However, fluorescence shows some interference because it is a quenching type, and the studies are in the excited state. So the excited state interactions are present in presence of lanthanum, samarium, and gadolinium. So we tried to have a practical application of this kind of sensing, and we studied with some tap water near our Rajabajar campus and groundwater near um, Sundarban area, and we have studied to find the recovery percent of these elements from the natural water that have been collected, and we can see that the experiment also behaves perfectly in presence in the natural water collected from the locality. The overview of this work is gamma irradiation irradiated nanocomposite set B is capable of sensing cerium 4, 3 and dysprosium at different pH. Cerium 4 can be sensed at pH 7, 2 and 12, whereas cerium 3 can be done at 12 and dysprosium at 2. If there is a mixture of all the lanthanides, is it possible? Yes, then it is also possible to add solution to pH 7 to calculate the amount of cerium 4 first. Then we can estimate the amount of cerium 3 with the known amount of cerium 4 at pH 12. Finally, the amount of 3 can be calculated at pH 12, knowing the amount of cerium 4. Therefore, interferences can be easily neglected by varying pH of the solution. This is the overall outlook of the whole gamma irradiation work. In situ radiations are more effective in generating nanoparticles. This is the flashback work outlook. Nanoparticles generated in presence of external gamma radiations may offer higher activities. Nanoparticles may be recovered from the reaction medium using gamma irradiation with higher reaction rate. Gamma irradiation induces higher electron density in the medium owing to radiolysis, which may offer altered reaction path. So this is the work done by my powerhouse, my students. And this is the funding agencies. I would like to thank, my personal thanks are to Professor Dr. Abhijit Saha, who has encouraged me a lot for doing this kind of work by funding my projects, being there anytime, any experiment, and being a lot of mental support. And I would like to thank the audience for patiently listening to me. Thank you again, Abhijit and Shukalpadi and Professor Director and Dr. B.C. Day Engineering College for this webinar. Thank you all. I would like to answer any questions.
Thank you, Kamalika, for your valuable presentation. And I would request the audience, if you have any question, feel free to ask.
Actually, Kamalika, I would like to ask one question.
Yes.
So the actually very simple question I would like to ask is that suppose you are doing a normal studying a normal nanomaterial, nanocomposite or something without doing any gamma irradiation. In that case, what difference do you notice in the morphology or the structure of that nanoparticle? That is the
Yeah, actually, you can carry on with your work without gamma irradiation. If the purpose of your application is solved by that, it's very good, fine and okay, no problem. But if that is not served, then please go for gamma irradiation. You will definitely find a difference, because first thing I have repeated many times, that there is a reduction in the size of the nanoparticles after irradiation. Many times we have seen. That is one observation. Second observation is that the surface activity of the nanoparticle increases because of the potential energetic beams and the excess of the free electrons present in the medium, which are eligible to reduce something or do some kind of chemical reactions which you wanted to do but were not happening in presence of, in the absence of gamma irradiation. So in those cases it is very helpful, but it also may not help you in certain cases, but you can check always.
Thank you.
Or any question? Kamalika, I have a question.
Yes.
That this that your work on that, there are different drug production and everything. As your material, is there any anti-tumor activity? Have you seen it, or
Yes.
anti?
Anti-tumor, yes. There is one, this is apart from this gamma radiation thing. There is one mesoporous alumina nanoparticle system that we have produced in our laboratory, and that had shown some anti-cancer, anti-tumor activity with some HCT and HEK liver cancer cells. And yes, they have shown.
Most of the palladium and platinum complexes, they have an anti-tumor property. That is, if they serve as a medicinal purpose, that they have some property. And your palladium is in your that you work with palladium. So for that reason, I am asking you.
Yes, palladium, platinum, everything we can do the biological work. A lot of work can be done. That part remains unexplored because that is the most unfortunate thing, that we do not have biological collaboration. And it is also a true fact that if we generate the nanoparticles, uh, we have many times we have supplied it to the biological collaborator, talk to them, but somehow or sometime they have either uh, left it for long, that has damaged or something. uh, it has not clicked some, but one work we have quoted, which is the mesoporous alumina, that was for the HEC and HCT cells, but other things. And because the chemistry part is in our hands, we can produce, we can see their chemical application as and when required. We have our own pace, we work fast, we write fast, we publish fast. So that is in our hands. So if we wait for the collaborators for years, 5 or 6 years have passed for the biological results. So with yeah, utter frustration, we have left the collaboration idea.
Exactly. Acha, I just see the chat box. This, acha, Suranjan Haldar. Acha, see, he has a question, ma'am. Can you tell me about uh, targeted therapy which helps cancer targeting cell? He asked the question.
Yes, for cancer cells, actually, beta or alpha emitting isotopes are very helpful, and we would not like to expose all the normal cells of the body to the high energy alpha or beta emitting isotopes. So we would like to have the only diseased cells in front of the uh, radiations. So that is why targeted therapy is used only for the cancer cells. Say, for example, someone has a cancer in the liver. So we would like to have our alpha or beta emitter radioisotope to be delivered directly to the liver. For that, we have to do two things. Firstly, we have to make a complex of that alpha emitting radioisotope with a molecule which has preference to go to the liver or to the thyroid, or say for example gallium citrate. This kind of compound has the tendency to go to the tumor cell only. So this is called the targeted therapy. So different specific type of cancer has different type of specific molecules which directly goes to that particular organ, avoiding other normal organs. So this is targeted therapy.
Thank you. Or anybody have any question? So, anybody have any question? Thank you very much, ma'am. And now over to Abhijit. Actually, we have some appreciation certificate that
Yeah, just I have an appreciation certificate for our speaker, Kamalika Sen. So
Thank
just
you very much.
please wait. This is a small token of appreciation for you for a nice lecture. I'm giving you time, precious time. So this we're going to send it to you, of course. Thank you.
Thank you so much.
Thank you. So our so second speaker, respected Dr. Abhijit Saha has joined us. He's, as you know, the director of DA CSR Salt Kolkata. So a brief introduction will be given by Dr. Shukalpa Dev for Dr. Abhijit Saha. Welcome you, sir.
uh, thank you very much. Uh, Next speaker, our respectable sir, Dr. Abhijit Saha. He is the director, center director, DAE, CSR Kolkata. So thank you, sir. And he has vast research experience over the nanotechnology. So over to you, sir. Please deliver your lecture. Thank you, sir.
Yeah. May I start?
Yes, please start.
Yes,
Yeah,
yes.
thank you. Thank you. Good afternoon. It's a privilege that I am been invited to deliver this webinar. So I really are thankful to head Mr. Ghosh, R&D of BC College, and other faculty members of this department. So may I start, because the topics which you have already highlighted, that it is basically the nanoscience and ionizing radiation and nanoscience. These are the combination of the two. And my previous speaker, Dr. Kamalika Roy, has already explained everything, so I could not attend. So sorry, Dr. Kamalika Roy, I could not attend the last year talk. So may I start my presentation?
Yes, yes.
Yes,
Yeah.
yes.
Okay. Thank you. Yeah. Well, just a minute. Is it?
Yes,
Is it
yes.
okay?
Yes, sir. Yes.
Okay.
Yes,
Okay.
sir.
Okay, fine. So this is the disadvantage of this online program, because otherwise I could have been happy to be there in Durgapur, because one of my very known place, and I like the place also, Durgapur. But unfortunately, I will not be able to see in the audience. So anyway, forgive me for any lacuna in this part. So my topic will be just a glimpse of applications of ionizing radiation in nanoscience. And so since it is a college and I expect that many students will be attending this webinar, so for that I just try to give the idea that what is the nanoscience. I'm not sure whether Dr. Rai has already covered, but just from my side I like to add these are the basic part of this nanoscience research. So the nanoscience is a very unique science in the sense that it combines many disciplines, not only that you have to be in the physics, chemistry, like there is all borderlines are actually vanished when you are working in the nanoscience, because from all branches people can contribute to this particular area, whether it is a physics, chemistry, engineering, science, technology, biology, medicine, all the branches. So it is a very unique combination of many disciplines. You can say is a nanoscience. So if you look at the very old scenario, many of you also possibly have seen these things. This is a cartoon which are available in the public domain. You can see also, but it was published in Nature 2006, based old publication, but it's a very meaningful for the new students who are actually maybe interested in future in the line of this work. So where that you can see that nanostructured materials are actually started a long time back. It's not a new science or new, what I mean is new area of research actually. But because of the new developments and technological developments, and these things we are now able to see more minutely or look into the details of the structure of these nanomaterials more minutely because of this advancement in the technological area. So because of the what I meant to say that high resolution transmission electron microscopy, the FEACM field emission scanning electron microscopy, these are all very latest techniques which have actually enabled us to understand the materials, how these things are actually produced. So these are the produced a long time back. I just took to give a glimpse of these things. These things is the Middle East time when this particular sword, which is called the Damascus sword, which was made by this carbon, multi-wall carbon nanotube cementite. So these are the things were used that time to manufacture this kind of steel, which this basically the steel which you consider the wood steel, which are in the southern part of the country, is on the Andhra Pradesh, where it is called the ukku. So basically, it was prepared. It was prepared there only. So it is a steel, but it is the uniqueness is the strength and sharpness. It can cut silk material. In fact, in the very precisely in the two parts like that. So it is a very sharpness and the strength of this material, which could made by at that time. You can see this is 1500, 1700 AD. So, and if you look at this pillar, which is we can always, when you go to Delhi, we can see this pillar as well. This is were erected by Chandragupta Maurya. So,
one second, Abhijit, are you showing your slides, moving your slide?
Yeah.
But we cannot see.
Oh, here is the full screen. It is there.
No, actually, you may have presented a window.
Just a minute.
Have you selected present a window?
Yeah, that's what I have done.
So if you select present your whole screen, then only we can see.
Just a minute, let me see.
Kamalika, it is coming.
Huh?
Coming, it is visible now. Nanotechnology and in India, that is coming.
Just let me see. I can turn once more. Is it not visible?
Yeah, it is visible.
No. Full screen because.
Full screen is not coming. Full screen is not coming.
Okay. No. But I tried with the full screen, but it did not. Just.
You can only share your.
Yeah, I understand your things. Let me. Just. No. Is not coming. I'm not able to select the files if you go to the full window. If you go to the full window, you're not able to select the file. Just
it is better you keep the open that this is open.
Yeah,
in the background.
Just a minute.
Yeah. Now it is coming. Yeah.
No, but it is not the full window, no?
No, full is not coming.
That is one. Wait, I'm trying to come to the full window. It's not coming. Excuse me, just.
Yeah, it is. Okay.
normally it comes automatically, that screen comes, but here the screen is not coming. Just a minute.
কাউকে ডাকছে।
আপনি এখন যেটা দেখছেন it will come, জিজ্ঞেস করেন তো।
Is it coming now?
Yes, 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 sir. Please go ahead.
Full screen.
Full screen is coming here.
Okay, okay, thank you. Yeah, thank you. Sorry for the disturbance. Okay. Anyway, so here we were actually. So this was the column pillar which we have seen from the Delhi. That this is the corrosion resistance materials which was used at that time. It's a long time back. You can see the 375 AD. That time also people have used this kind of mesovite, these iron oxide materials, which are basically iron oxide nanomaterials, which are used, and these were actually the corrosion resistance. So many years have been passed, but it is still as it is. So there is a resistance materials, the corrosion resistance materials are produced by the combination of this kind of materials. So these are the things, and this is also many of you have already seen these things. This is in the chart as you have seen this color, and we can see this color when you see from one side by illumination with light, but when you can see also the same materials which can show this kind of color. So it can be red as can be green. What is my point is that materials is same basically, only the materials which are silver doped materials, which are actually the same composition wise same, but the size of these materials are only is an important parameter. This is which we could see from the nanoscience, which you all of you that is a Feynman who started predicting the possibility of maneuvering things atom by atom. So we can reach the nano size regime if we can combine the different size of different atoms. So that was the first statement made by Feynman. And first experimental observation was made by Faraday when he prepared the gold nanoparticles, and it is still there in the and published in 1857. This is what I try to emphasize, that the particles being at the same time very small as compared to the wavelengths. And here is the most important point is that a mere variation in the size of these particles gave rise to a variety of resultant colors. the colors which you could see, the cups, the two cups which one green on the red, that's just because of the materials particle size of the was of the different sizes. So if you can simply vary the size of the particles, you can get the different colors. So that is what is important here. You can see here, these all materials are same, but the colors are different. The difference where? The difference in the size of the particles. So these are the things that's very important, that how the size can be controlled. This is when you are preparing this material, the size of the particles are very, very important. Normally, when we use for other things, we do not consider much about the size of the part. But when you are working in the nano size regime, then we have to be considered. We have to consider the size, not only the size. Then another important parameter comes into play. There is the size distribution. The reason is the size distribution is that when you prepare the materials or synthesize the materials, all particles cannot be of the same size. So always there is a distribution of the sizes. So suppose if you can make particles of 10 nanometer, all particles in the same synthesized materials cannot be the 10 nanometer. It can be less than 10, it can be more than 10. So there is always a distribution. So distribution in general, it is the Gaussian nature. So it can have the average value, and then we can have the spread of the value. So suppose 10 nanometer minus, suppose maybe 8 nanometer to 12 nanometer, then we can say 10 plus minus 12. So sorry, 10 plus minus 2. So that is what we can say. So always there is a distribution of the particle size. So objective will be how narrow we can narrow down the size distribution. So suppose if I say the 10 nanometer, it can be close to the 10 nanometer. So whether maybe 10.2, 10. Or 9.8 or something like that. So as close as you can come to the average value, then we say the particles are very good quality, and then we say also the particles are monodisperse. Otherwise, particles are polydisperse. So this is what is a very, very important parameter, important aspect, which always you have to come into mind, because when we are working in the nano size particles. But what do you mean by the nanoparticles basically? This is what we call, say, size between 1 to 100 nanometer, and this is a 1 billionth of a meter. And just to give you an idea for the students, basically, the size of the hydrogen atom is only 0.04 nanometer, whereas the size of the protein molecule, suppose in biological system, 1 to 20 nanometer, and computer chips is around 180 nanometer. And if you go to the diameter of a human hair, it is a 10 microns. So this is the roughly visibly you can see what is the dimension of each things. So nanometer is much lower than this. So this is the hydrogen atom, and after this is the protein, and you can say the nanometer is in the size regime of the proteins molecule, the biological molecule, which is nature prepared in our body. So at the nanoscale, physical, chemical, biological properties of materials differ in fundamental and valuable ways from the properties of the individual atoms and molecules or bulk material. So this is where the nanoscale size is very important to all of us. And to have a rough idea, the nanotechnology, when you can say, is basically the term used to describe the creation and exploitation of the materials with structural features in between those of atoms and bulk materials, with at least one dimension in the nanometer size regime. And if you have the rough idea, that is what I've said, it comes around the protein structure or the DNA, this kind of structure size of the same. And interesting thing is that if you have the particles, and the particles can be of the smaller diameter, can be the bigger diameter also, but the surface area also gets changed. And that is another important issue we have to keep in mind, because nanoparticles exhibit unique properties due to their high surface area to volume ratio. If you calculate these things, a spherical particle has a diameter d of 100 nanometer. If you calculate the students can easily calculate what will be the volume of this and what will be the surface area of this. And if we divide surface to volume ratio, you'll find it is a very large. So this gives an approximate surface to area volume ratio of the order of 10 to the power 7, which is significantly larger than the macro sized particles. So this is where I was telling the size is important. So if we have the big particles and if we make it smaller, then automatically surface area goes up. And once the surface area goes up, the surface to volume ratio also goes up. So once the surface to volume ratio goes up, the activity of the surface energy of the particles also enhanced. And once the surface energy goes up, the activity and other stabilization process also comes into the picture. So this is what generally accepted materials properties are derived from the bulk, where the percentage atoms of the surface is minuscule. These properties change at the nanoscale. So I try to highlight that how the nano size domain is very, very important for even for our applications. These are commercially nowadays we can see everywhere, almost starting from the air conditioning machine to the paint materials, to the textile industry, to the LED and optical amplifiers, the telecommunications, the solar cells, the sensor materials. These are all places where actually now nanomaterials are being directly used. So these are the commercial utilization of these materials are nowadays becoming very, very important. So this is a very frontline area of research where the students can also enter and can contribute a lot in coming future. Now coming to my main topic, as you have mentioned, there's the radiation is part, and I'm sure Dr. Kamalika has already explained this one, because radiation facility means it can have the, I have given the topic that ionizing radiation. Ionizing means suppose we can see with the light. Without light we cannot see anything. So light is another source of radiation. We get it from sun and thing, but these lights and the other light, the ionizing radiation, is slightly different. Because the light which you see with the UV, ultra, mostly the visible light with which we can see, the eyes can see through that light only. That is a very, very, you can see the wavelength of that, or the energy of the photons of that light is only a few electron volt. So the energy of the visible light, whereas energy of the ionizing radiation is very high, maybe million electron volt. So almost 10 to the power 6 times more than our normal light. Whatever the light we use in the electric bulb or tube, fluorescent tube, we get it. So this is a million. So energy is very, very high. And this energy can be this high. It comes from the two sources. The ionizing radiation means this can interact with the material and can ionize the material itself. So suppose it is the atom, then it can knocks out the electron can also. So ionization means with this high energy radiation, the ionization can take place in your material. So that is why it's called the ionizing radiation. And gamma is one of the simplest example I can say, because it is available in our lab. So this is basically the cobalt-60 radioactive isotopes, where the cobalt-60 is a 60 by 27 if you consider, then it has the 2 beta and then is gamma. And whatever we have said, we have studied in our school level, then we are used to know that there is radioactivity, and radioactivity isotopes are never stable. It always disintegrates, spontaneous emission happens, and we get either alpha, beta, or gamma. The alpha, beta are basically the charged particles, which have the positively charged, or beta is the negatively charged, alpha is the positively charged, doubly charged helium ions, and beta is the negatively charged electron, and gamma has no charge. So it's a neutral. So an advantage is of gamma, so it can penetrate to a much larger space. So that is why I call this gamma is a high energy radiation which can penetrate to a large extent, and that is why the gamma is also used in radiotherapy in the cancer treatment. Because cancer treatment, you have heard the radiotherapy, they are the cobalt-60, cesium-137, different radioactive sources are used, or the electron beam like linear accelerator are also used for the treatment of the radiotherapy of the cancer. So this is a gamma which can be detrimental to our system, but it can be very useful for our system as well. So this is what I try to show, that this gamma radiation, of course, when we are handling, when we are using this source, it has to be in the shielded form so that there should not, activity shouldn't come out. So this is the two photons, basically 1.17 and 1.33 energy of photons comes. Average energy, if you can say, 1.25 MeV. And cobalt-60 is the source, its half-life is 5.27. And this is where we can put in our chamber also. We can put some optical fiber and also do some measurements online. So if it is the radiation field, and we can do the other studies also in this thing. But the gamma chamber inside is like that source is here, and the if you put your samples here, and it can go down and can be here. So it is in the reactive field. So now, question what I was telling a thing, and when the gamma falls into any materials, so what are the possibilities of interactions? So it can interact either in the photoelectric effect, or it can be through the Compton scattering, Rayleigh production, on photonuclear reaction. These are the mostly. But the photonuclear on this energy is Thomson elastics or Rayleigh coherent. But if you look at most of the chemistry, biological works involves water. So I'll take the example of water, but it can be any other material as well. How does this photon interact with this water molecule? Basically, it interacts through the Compton scattering. This is through this method. This energy, 1.25 MeV of gamma photons, it interacts with the water through the Compton scattering. And this is what happens when if you have the water, and if you put the gamma radiation in water, it ionizes, knocks out the electron, and it happens to be in the 10 to the minus 16 second. So that means it's called the femtosecond time scale, and then it stabilizes, gets to the microsecond time scales, and then the electron gets solvated into the medium. So if you have the water where you can generate this electron, the electrons will be finally surrounded with the different water molecules. So this is called the, almost you can say, in a cage, your electron is sitting there. And that happens in this thing. So this is a sequence of events which take place when the high energy radiation falls in water. So water interaction with these things. So this is a just example. I've taken water because of this biological or the chemical importance, because mostly people are using it, and also for processing, water is one of the very good solvent. And now there are different approaches how the materials can be produced, which can say the top-down method or the bottom-up approach. And top-down means you have the big particles, you have to just break it physically and make it smaller so that its particles come below the 100 nanometer or so. And also bottom-up approach, that you can start from the ions or the atoms and build up to come to that few nanometer size regime. So there are different ways people have been doing right now: lithography, atomic force manipulation, aerosol spray, gas phase condensation. Whereas the bottom-up approach is being taken as a reverse micellar system, sol gel process, hydrothermal synthesis, irradiation route, template assisted gel. There are many options there, but I'll just try to focus on the irradiation route because our mostly topic. Anyway, so now is coming to the what are the advantages of the gamma irradiation route? Because what I've shown, the selected solvated electron is generally uniformly and controlled way you can produce, which can be useful for processing the materials. When you process the materials, whether it is the polymer materials or things, processability is most important nowadays for direct commercial applications. And that is what you can do if you have the medium. So medium can be of the different ways, but it can be taken as an electron, which is actually is called the soluble electron. If it is in water, we can hydrated electron, or it can be in different solvents as well. So the method is highly reproducible and gives a narrow size distribution. Synthesis materials are free from any undesired products because you are using the electron directly into this system, into the whole reaction process. So that's why the material does not contain any other undesired products. Suppose you want to reduce any metal, suppose metal ions are there, suppose silver, for example, we have taken, then you want to reduce it to silver 0. So silver plus 1 to silver 0. So that means you have to give feed electron only. And that is what you can do through this electron, which is generated from the radiolysis of the water. So that electron is free. So, but when you normally otherwise what you do, you use lithium aluminum hydride, sodium borohydride and all this thing. And that remains in the medium. And that has caused the further processing and all this thing. So this process is considered to be one of the cleanest method for synthesizing the materials. And this is what example, the silver, initially it is silver nitrate, there is colorless and it becomes a color. And here, there are two other more important aspects coming into the picture. What do you say when you say that high dose rate and the low dose rate? A high dose rate means, suppose it is a photon I said that is a gamma is basically the electromagnetic radiation. So it is a photon. Now photon, when it falls on a certain area, then it's called the flux. We have to measure it number of photons per unit area. And this is what when the it comes when unit area, and but the time, how many photons are actually coming in a certain time. That is what is called the dose rate here. So if the number of photons, very large number of photons, that means gamma photons are coming on a very short time, they call it a high dose rate, but it is an otherwise it calls a low dose rate. Now, and that is basically nothing but a photon flux. How many photons per square centimeter area per unit time? That is what is called the photon flux. And that can also have effect in synthesis of the nanostructured materials. And so if you have the high dose rate, then you can have this kind of structure, more uniform there. And if you low dose rate, you have this kind of much bigger structure, whether it is a smaller structure. So the uniformity in smaller structure, high dose rate is desirable. Low dose rate, it can give it a much bigger particle size. And this is what you can get also bimetallic nanoparticles you can develop. Suppose you have one particle metal, then you can combine with another metal also. So that is what's called the bimetallic materials. This is what's called the gold and suppose lead. You have the gold lead. Gold is inside the core, inside the things, and shell is made by the palladium. And this is formed due to intermetal electron transfer from palladium to gold. So this is a standard reaction process. So where you can get from gold to palladium core shell structure. But if you go for the high dose rate, then we can have the alloyed structure, not the core shell like structure. This is an alloyed, a mixing of the crystalline materials. So this is the alloyed structure formed due to a reduction of both is more faster than the intermetal electron transfer. So here it is happening when the core shell structure is happening, it is called the intermetal electron transfer. But when the high dose rate, it is intermetal transfer is slower compared to the direct reduction of gold and lead. So then you are getting the alloyed materials. So whether we will get the alloyed materials or the core shell like structure is a basically bimetallic structure. So that you can see using the radiation, we can get different types of materials and different sizes of the materials. This is one more example. So this is where you can get the composite materials with the polymers. So the palladium is the polyaniline. This has been the nanowires like of structure, where the particles are formed in these things uniformly distributed over the nanowire. So this is also produced through the radiation routes. And these are all characterized through the XPS, X-ray photoelectron spectroscopy, then TEM and FESEM. So this is the thing, you can see the polymers is there inside, and that has been allowed to grow to make it. So this is the monomer. Suppose polymer, the polyaniline, if you take the aniline and then if you polymerize, you will form the polyaniline. The polyaniline is a conducting polymer compared to our normal polymers like polyaniline, polyphenol chloride. But polyaniline, these are all the insulating material. Mostly the polymers are insulating material. But polyaniline, like there's few which are very conducting materials. So polyaniline is one of the conducting polymers. Here you are taking the monomer, we are allowed in the radiation field to grow in the form of polymer. So it's polymerization taking place in the is the oxidative polymerization is taking place, and oxidative polymer gamma catalysis with metal precursor. Then we are getting this kind of structure. So both polymerization and metal are inside the things. Metal particles are also formed. So both processes are going on in the same radiation field. So this is a very, very interesting observations and work. So this is another example. I said that there's a glimpse of the examples. I said, particularly don't have to go through these things. You can have some idea on things later on. If someone is interested to work in this area, can read the literatures and try to get more information. So these are the things where you have shown. This is what is called the dendrimer. It's also a polymer, but this dendrimer, it has a special advantage compared to the other polymers. This is a branched like structure, like branched structure. So this is what is happening in case of the dendrimer, but the advantage of that, all the polymer chain length is same compared to the others, other system. This dendrimer is different, and dendrimer has the advantage that it is biocompatible, and not only the biocompatible, it is being right now, it is clinically being used in the drug delivery. So this what we have tried to show how the particles can be grown inside the dendrimer through the radiation route, and we have also made it through the other chemical route. But what we have found, if we use the radiation route, we can get the different structure compared to the other normal chemical route. So here, what we have taken the thiosulfate of things, then electron, and producing this kind of CDS. Suppose this is a CDS, and these are the book which you have written there. You have published in the CRC press, where you have given details of these different types of materials which we could synthesize using the radiation. And this is examples where you have taken, here is the atomic force microscopic image, where you can show this long range structures can be generated because through the radiation route, but unlike in the chemical route. And when we have start the dynamic light scattering measurements, we could find the different clusters are formed actually in the sample. That we could get 5.3 microns length of structures. So this is assembled structure we could develop using the radiation, unlike in the other chemical route things. So this is where is the uniqueness of these things. And we have also made one work is the gamma photons. This is where we have synthesized. Now we are trying to see how the photons can also affect the nanostructured materials. So high energy photons can be useful for fabricating the materials. Also how the materials, and suppose you are using in the reactor system, where the radiation is coming and can damage your materials also. We have to look how the materials can be damaged by the radiation also. So both aspects are also equally important. So one of the impact of gamma photons on the nanoscale of tungsten sulfide. This is a very important material. It's basically 2D TMDC materials. Here you can also introduce the magnetism into this kind of materials. So, but here what we have done, we have shown this is the impact of gamma photons, how the structural changes have happened with the radiation. And there's a layered morphology, and there's evidence exfoliation. And so this is slightly complicated, so I don't want to discuss much here, particularly for the students, it may be too much for them. There's what is the nature of point defect? Because when the materials are there, and if you put the radiation, the crystal structure may be damaged. Suppose if you have the crystal structure, if you consider as a cubic structure, like in a room, so all in the corners there are atoms. The different atoms are actually combined in a certain bond. There is ionic crystal here. But now, if you put the high energy, it can create the defects into the crystal structure. So those kind of studies are actually being done through these techniques. So different results are there, but I don't want to go through those things. These are okay. So anyway, so this is another examples which I can show how the radiation, especially gamma radiation, can be useful for phase transition of the boron-related nanoparticles. So if phase, which are talking of the crystal, so crystal can have can be in the different phases like cubic, hexagonal, monoclinic, the different phases of the crystal structure. Any crystal material can be in the different classified. It can be in the 6 classifications are there. Now, whether this phase from one phase to another phase, it can be transformed or transferred using the radiation. This is what we have shown here. These are boron nitride particles. Here's the phase when there is a cubic to things. But these boron nitride particles is a very, very important material in the sense is used in the lithium batteries, because nowadays we use all the places lithium batteries, and so is a mobile or any other computer or things. So these are lithium batteries, which is fast dissipator with low thermal expansion. So that is what is important in the boron nitride materials. The importance of boron nitride materials, it is used in lithium batteries as fast dissipator with low thermal expansion. So because of this thing, boron nitride materials are very, very important. Now, whether these boron nitride materials can exist in the cubic phase or it can be the hexagonal phase. So when you are hexagonal phase, we are irradiating, it can be transformed in the cubic phase. So this is one example of the boron transition. Now coming to the another example where it can be very, very useful for biological point of view. That is what I've said, that gamma can be useful for cancer treatment. That is what radiotherapy is being used in most of the hospitals nowadays, almost. So there is a radiation therapy and then gamma source is required. And the same gamma source can be useful for identifying the radiosensitizer point of view, because gold nanoparticles are considered as one of the radiosensitizing materials. What do you mean by radiosensitizing? Basically, radiosensitizer means you have, because when the radiotherapy or the cancer treatment takes place, you have to give the radiation dose into your cancerous cell. So the cancerous cell gets affected or the killed because of the radiation. But the problem is, surrounding the cancerous cell, there are many, many normal cells, biologically active normal cells, which also get damaged. So that is why it's always objective how we can minimize the amount of dose. We can use a very low dose so that it can kill the cancerous cell, but it is not significantly affecting the normal biological cells. So that is where is the importance of the development of radiosensitizers. So radiosensitizer basically role is that it can reduce the dose amount, because it itself, it can sensitize the cancerous cell through the radiation. So that is what is the radiosensitizer. Like in case of photodynamic therapy, is called the photosensitizer, and it's the radiotherapy is called the radiosensitizer. So radiosensitizer gold nanoparticles have been found to be the one of the very promising materials as a radiosensitizing materials for radiotherapy treatment. And this is what it has been taken, the polymer grafted. This is a recent work published. So this is a well-defined polymer grafted gold nanoparticle was synthesized and studied under gamma radiation to better understand the involved radiosensitizing mechanism. So here gold nanoparticles is there, and then we are putting the radiation, and there is a grafted polymer materials which can also degrafted. So degrafting means the polymers are detached from the gold nanoparticles. So what are the sites where from that it has degrafted, degrafting has taken place? That gives you the idea where is the radiosensitization active sites, what are the active sites of the radiosensitizing materials. That gives, you can get some idea about that. So it was aimed to quantify and to localize the radiation impacts on the grafted polymers, revealing the production sites of reactive species around the gold nanoparticles. Because when the radiation comes and falls on the gold, the radiation does not directly kill the cell. It first absorbed by the gold particles, it generates the secondary species, and that can actually kill the cancerous cell. So that is, if the gold particles are very selective, it has a very selective and it can selectively binds with the cancerous cell, then radiation will fall onto the gold particles, and those particles will only damage the cancerous cell, not the other normal cells. So that is the objective of development of this kind of materials. And so this is the potential to add bioactive molecules such as anti-cancer drugs have been explored by grafting doxorubicin onto the polymer corona. So this doxorubicin is also called the another anti-cancer drug. So there are many anti-cancer drugs which can also bind on the surface of the nanoparticles. Nanoparticles, which I said that in the beginning, the surface to volume ratio is very high. So automatically it has a large surface area where you can have the large number of groups like drug molecule, cancer drug or other drugs can be put under the surface of the particles. So you can have the large number ensemble in a very small area. So that is what is the advantage of using the particles for many application in the radiation treatment. Now, Dr. Abhijit Ghosh has said that when we are talking, just to mention that what are the facilities available in our consortium here, particularly in Calcutta Center, and in which way we consortium helps supports the research activities of the different universities and institute. So in that context, which I mentioned that we have the facilities which you have, that anyone can come and can use it from the university or the colleges. Researchers can come and use our facilities. that is called the one-time use of facilities. And also it can have the collaborative research scheme, which we have found that we have the 3 years terms. We normally support the projects where we can be the research scholar, travel support, consumers and things. So most of these proposals lead to fulfillment of PhD of the research scholars. And so these are the way consortium supports the research of the colleges and the universities. As Dr. Abhijit Ghosh has mentioned in one of my conversation, that to mention this one at the end of the talk. So I am just trying to push these things. But before that, these are the other things. But before that, I'll come to this talk end of this presentation here. So if you have any queries, we can do, or we can end up the whole talk. I can be available for the any queries to answer. So, and our facilities which you have, particularly in chemistry lab, here we have the fluorimeter, fluorescence spectrophotometer. We have the UV's NIR spectrometer, which is ranges is very high, 175 nanometer to 2000, more than 2000, I think around 3000 nanometer. So it's a long range structure we can do. We have that lifetime measurement setup, using the photocorrelation system, and this is what is a combined system. Basically, you can measure the static fluorescence as well as lifetime measurements. Both can be done, and it can be done from 25 picosecond to 1 second. So low, and it has also the emission. Also, we can measure from the ultraviolet, visible, and the NI range also. And this can be, so this is a very versatile system we have here. And then we have the FTIR, the Fourier transform inspired spectrometer. This is the Perkins frontier machine. Earlier we had the Spectrum GX. Now we have just recently replaced with the frontier machine. This is also, we have that mid IR, far IR, and near IR range we can cover. And also we have the total reflection HATR facility, which is also useful for measurements, particularly for the thin films, which you can measure with using the setup. Here also, we have this kind of accessories available with us. And normally the IR, we use a KBR window, which is potassium bromide window, but potassium bromide window is very hygroscopic. For hygroscopic material, it is not useful. So we have to use the zinc selenide or the calcium fluoride window. These are all available to lab. Then we have the dynamic light scattering setup, through which we can measure the size, because we have talked about the particle size. So this is the size we can measure. Transmission electron microscope, one of the way, one of the method or the technique through which we can measure the size of the particles. X-ray diffraction also we can use to see the crystal phase and size of the particles. And in addition, we can have the dynamic light scattering also we can use to get this idea of the size of the particles. So besides size of the particles, we can get the idea of the molecular weight of the materials, and also the jitter potential of the particles. Particularly jitter potential things comes because for the students I can just mention is a slightly newer term. So jitter potential means is a particles which you suspended in the water or the medium, then you can see it fluctuates because it cannot be stable in a particular position, because all the water molecules start bombarding on these things. So this is basically the fluctuation which takes place, and if you put the light, and you will get the fluctuation of the light intensity. That is what is the dynamic light scattering particularly works in this principle. So it should be in the colloidal phase. So dynamic light scattering measurement, which is also called the photocorrelation spectroscopy, and that is also depends on particularly particles which are in the colloidal phase. You can see this thing Brownian motion, because all of you have read possibly the Brownian motion in the school book, and the colloidal materials are there, and then true solution, colloidal solution, and not a true solution. That is so Brownian motion basically takes place in the colloidal sample, and that you can size it will determine. It depends on the temperature, viscosity also important, because the medium also very, very important, and temperature is proportional to diffusion rate. If you increase the temperature, diffusion will be faster, and that you can get the idea. And this is roughly the idea of how you can get the size of the particles. This is called the Stokes-Einstein relation. Is a D, and is a viscosity is a term, and the particles radius is the term. And here is the correlation function is there. You can, this is nowadays available commercially. Otherwise, you can develop this equation function using the different computer program, and then also you can determine. This will give you the idea of how the particles are there and what will be the size of the particles. And that is what I said. This colloidal means you have the particles on surface. You have the different layers of the medium. If it is the water, you can have the different layers of the medium. It comes the Stern layer, diffuse layer like this. And this is the area you have the potential difference between these two. Because particles once are formed on the top of the surface, it can be the positive charge ion or the negative charge ions. Always will be there. So that is what we can have the different potential difference between these different layers. Because close to the particles will be one case of, and as you are moving away from the particles, we'll have the different layer thickness, not in thickness in the sense of the charge of the thing. Charge will be vary from the close to the particles to the away from the particles. So this is called the diffusion layer, and that diffusion layer is basically called the zeta potential. The potential difference between this layer to this layer. This is what is known as the zeta potential. So that gives you the idea about the charge on top of your particles. What is the surface charge of the particles? Because surface charge is very important in the sense, because suppose your material surface charge is negative, then you consider, suppose for biological applications, so DNA, if you say DNA material, which has the component, our genetic material, which contains the phosphate. So phosphate is there, so phosphate is negatively charged. Even you want to put, like that what I said, the cancer drug or other things loaded by the particles, but if it has a negative charge, it will never reach the DNA. So you have to know the charge, what is there, and what is the surface charge of the particles. So that is where we can know the surface. And that is a zeta potential measurement techniques, how we can do this, a gold electrode, and then electron mobility we can know. From there we can get the idea what is the charge of the zeta potential. So that is the relations we have. We know this is already established relations things. You can use this relation and can get the idea of the charge of the particles. And this is we have the laser Raman spectrometer. We have the facility with the temperature controller things. We can measure from the liquid nitrogen temperature to the 600 degrees centigrade temperature. We have the polarization, where you can do the polarization measurement, and then we can also map the micro Raman mapping. Also you can do polarization means you have the particularly, if we have the polarized light, because these are the lights which we through which we see, these are not polarized light. It can be polarized light, it can be right circularly polarized or left circular polarized. So because of that, also the many properties can be studied. So these are the all advantages we have here, and we have the mostly we are using the helium neon lasers. And this, suppose it gives some examples of the particles. Suppose it's the graphene materials, which I have not talked about this today. So these are the surface we can really study it. You can take the image through this Raman microscope, and so this is a very, very important image. You can get idea what are the layers of things, vector measurements. All these things can be done with a very sophisticated technique. But I said in the beginning that that technological advancement has enabled us to study the nanostructured materials in much with greater precision, and to know the structure, how we can control the structure. All this is possible because of the advancement of this technological development. It's a very, very highly, and Dr. Bisra is an engineering college. I think if you have the combination of the engineering and the scientific, combination of the scientific people, I think you can do not many good works, or you can develop many things as well. So, and this is one of the ITC isothermal calorimeter, which is basically looks like it's very small, but quite expensive. It nearly is around 80 lakhs or so. So it's a very, very, but it can give you idea what the thermodynamics of the things. So all the thermodynamic parameter like enthalpy, entropy, and free energy changes, all this can be measured with this kind of isothermal calorimeter. It's a microcalorimeter, the very small things we can detect. Anyway, so with that, I should thank all of you for kind patience.
Thank you, sir. And if anybody have any question, please ask the question.
Sir, with kind permission, I would like to ask one question to you, sir. Is that how do you determine the amount of radiation which we can think of giving to the gamma radiation to a particular compound? Okay, and what kind of different radiations can be given to that sample? Which, if you can enlighten on that matter, it would be good for us, all of us.
Okay. So you have, what I understand, you have the two questions. One is on what is the amount of radiation, and what are the different types of radiation we can use. That is clear? Is it clear?
Yes, sir.
The amount of radiation, how we can measure, because that for that you need the dosimeter. So with there are different types of dosimeter. They are called primary dosimeter, secondary dosimeter, like that. There are, suppose like when you go to the TLD badges, suppose if you work in the radiation area, you will have the TLD badge called thermoluminescence detector, which is very small pocket type things, and that can absorb radiation, and that also can give you the idea how much radiation is absorbed. So that is a very protection for the human beings when they are working in the radiation field. This is the primary dosimeter, one thing, and this is called the secondary dosimeter, like for chemical dosimeter, which called the one of the most common dosimeter types called the freaky dosimeter, which is basically measures the conversion of the ferrous to ferric. So if we have the ferrous salt, like ferrous ammonium sulfate, so if we put in the radiation field, the ferrous will be converted to the ferric, and then that you can measure from absorption spectroscopy how much actually ferrous to ferric. So from there is a relation also how much the actually radiation dose has been absorbed by the materials to convert it to this certain amount of ferrous to ferric. So if you know the certain amount, how much amount of ferrous has been converted to the ferric, from there you can get the idea how much dose actually fall into your system per unit area, time. So time is a factor. Now coming to the different types of radiation, can be, this is just today I have talked, mentioned about only the gamma radiation, but I actually wanted to include the ionizing radiation, other radiation as well. I have not done because I thought time may not be things, and too many things at the same talk may not be too much for thing. So that is why I have converted only to confine to the gamma. But there is ionizing radiation called the high energy ion beams. The ion beams means suppose you have the one argon, and then you can knock out the one electron called the argon ion. So argon ion, when you knock out the ion, then it becomes the ions. And if you put the voltage across the things and you allow the particles to move into the certain voltage area, then particles get energized. And then particles, once they get energized, it can be in the low energy, or it can be medium energy, or it can be very high energy. Low energy means suppose it can be the kilo electron volt. Medium electron energy normally we work is a MeV range. So that ions, which are particularly the argon ion, carbon ion, all the elements can be basically ionized. And if you put in across a voltage, but you can do the pelletron, which is there in the Institute of Physics, Bhubaneswar, or IUSC, NSC in Delhi, or in TIFR. There's things, there is a potent terminal voltage if you put, and you allow the charged ions to move, then you can generate different high energy ions. So that can be also put into the sample and can be a different. So different ions can be generated, can be useful for studying the materials damage also. Many people are working on the lithography, particularly they use the suppose different ions and they put on certain materials, and then you can have the different areas impregnated with the different energy ions, and that is also called the ion beam lithography. So lithographic structures, suppose you can get using the different ions. So that you can get also using our VECC variable cyclotron center, where also you can get high energy ions you can get from the cyclotron. So different sources there, accelerated perchlorate is there, which actually produces the ion beam. So that is a atomic ions, some atoms gets converted into ions, and then it gets accelerated in this system, and you can get the different energy of ion beams, and you can just put your target or the materials on before your ion beams. So that is the one way of starting. Gamma, utilization of gamma is one advantage, is homogeneously distributed into the system, and gamma has a high penetration power, which is not possible with the other ions, because that can only penetrate up to a certain nanometer level or to maximum to the micron levels. but gamma can penetrate in the millimeter or whatever it is. So it is the gamma has the advantage of this kind of thing. But if you want to modify any surface, for example, I can just give you the example, can be very interesting also. Like suppose our lens which you put in the eye lens, which you put got the polymethyl acrylate. So what people have used, the research works on them. So the methyl acrylate, because we use the contact lens, when we have used the contact lens, many people find it is a itching problem. So then water comes out on things. So that kind of things people have studied, the polymethyl acrylate. There is in hydrophobic groups, basically carbon, methyl groups of things are projected on the surface. So they have used the ion beams to just chop out from that hydrophobic groups to reduce this itching problem on the contact lens. So that is what also people are using the ion beams. So if you want to modify any surface, you should go for the ion beams. But if you want as a bulk, you want to modify or you want to develop certain materials, you should go for the gamma radiation. That is what I can say.
Thank you, sir. From Suranjan Haldar, one of our participants, he has a question.
Yeah.
He asked that what is the difference radiotherapy and proton therapy, and which radiation is high and which is very good for cancer treatment?
Proton therapy or phototherapy? What is that?
Radiotherapy.
Radiotherapy compared to
Photon therapy.
Huh?
Proton therapy.
Proton therapy. Okay. Radiotherapy, as I've said, that's mostly are done through that gamma or electron beam. Gamma means cobalt 60 or cesium 137. These are the two radioactive sources from which the gamma emits, and the gamma can kill the cancerous cell. And where you can use the different radiosensitizers, drugs or other things to reduce the dose load to in the treatment. But that is what most of the hospitals, wherever you can go for the radiotherapy, these are the standard treatment technique. But but proton therapy is slightly unusual state now. Once upon a time, it became to be the very popular and thing is that because gamma, as I said, it can penetrate to a certain thing, quite. You can say there is a high penetration capacity, so it can penetrate to a longer time. Suppose if the cancer is inside the buried system, that it has to have gamma has to be used. But in case of proton, as it is a positively charged particles, you can say that it cannot penetrate to much extent, so it can only modify the kill on the surface. So if some cancerous things on the surface, the proton beam can be useful. But if it is an inside, then radiotherapy has to be used. Then gamma has to be used. So these are the two ways people have been using. But proton therapy is limited, not very popular. Even in India, is not there. There are some laboratories or some medical facilities they have that facility. Also, there are many other. There's a neutron therapy. Also, people have started working on that. Los Alamos and other places. So the neutron therapy, because neutron is also a neutral, so it can be useful, more efficient than a proton. But those are, of course, still now it is of limited use.
Thank you, sir, for your valuable lecture. And now, just before vote of thanks, our Abhijit sir, he just show the that is appreciation certificate.
A small token of appreciation for you, sir.
Okay, so I can stop sharing now?
Yes.
Yeah. Yeah.
This is a small token of appreciation for you, sir, for kind consent for giving the lecture and coming here, enlightening us on everything.
Yeah,
So,
thank you so much. Thank you very much.
Thank you. I would request Dr. Saurabh last now to maybe give a vote of thanks now. Yes, yes.
I would like both the and you some I would knowledge that our people once it for take thank you. I would like I would for yours I would assist if I contact and organize to make I also the what last time I see the I would like for the week and have once I hope teacher thank you. Thank you.
Thank you.
Thank you, sir. Thank you, Kamalika.
Thank you, both of you, sir. Thank you, Kamalika, also.
Thank you, Abhijit. Thank you, Sukalpadi.
Thank you very much.
Thank you.
Feedback. Just a minute. We share our feedback form.
Okay, thank you. Kamalika. খুব ভালো হয়েছে presentation. Thank you for joining.
আর বহুদিন বাদে কমলিকাকে দেখেও আমার খুব ভালো লাগছে।
অভিজিৎ দাকে বলি সুকল্পাদি আমাদের কলেজের সিনিয়র। আমি এই ওয়েবিনারে
এইমাত্র জানলাম।
গেলাম।
শুনলাম আর কি, আমি জানতাম না।
কলেজ মিন্স
ভালো লাগছে।
হুগলি মহসিন কলেজ।
আচ্ছা, হুগলি মহসিন কলেজ।
হুগলি মহসিন কলেজ।
ওকে, ভেরি গুড, ভেরি নাইস।
আর অভিজিৎ তো ক্লাসমেট ছিল।
সময় হলে এখানে আসবেন, দুজনেই আসবেন।
আপনারা আসবেন স্যার, এই প্যান্ডেমিক সিচুয়েশন ওভার হলে।
Yeah. I love to go there because once upon a time I was used to quite conveniently to go to Durgapur near the Bidhannagar area. My relatives stay there, so I'll be really happy. Yeah.
Well, Saurabh sir stays there actually. Saurabh sir ওখানে থাকে।
Okay. Okay, thank you so much. So you try to visit our place also, consortium here, Calcutta Center, and try to utilize whatever possible. We can also will get the support from here. So that is always we try to extend our support to college and university. So we really welcome all of you. Whenever you research, just drop a mail. That will be good enough for me to proceed in this fashion. So that's and it is really heartening that you have arranged this kind of webinar things, and which is slightly unusual for many of us because radiation is not very common for any material science. So this is one of the things I think you have chosen one of the promising topics in recent years. So I really thank to all the organizer members and things.
Thank you.
Thank you so much.
Thank you. Thank you so much, sir.
So may I leave now?
Yes, sir.
Thank you so much.
Kamalika, please send the yeah, ठीक है.